Hello everyone and welcome to lecture 15, renal clearance. Okay, so first I want to talk about the relationship between filtration and excretion. So as a reminder, filtration occurs at the beginning of the nephron, so when fluid is first entering into the nephron through the glomerulus. Alright, so that's the initial part of the nephron, and that's the only place filtration takes place. Then it's going to go through the nephron and ultimately end up in the urine, and we call that excretion. So if it ends up in the urine, it's called excreted. So really what we're going to talk about now is when some substance ends up being filtered into the nephron, all right, and it gets processed and goes through the nephron and ends up in the urine as being excreted. And I want to make a comparison between how much got filtered into that nephron and how much ended up in the urine. So this is why I need these formulas here. So we call something called a filtered quantity. And you'll notice the units are in milligrams per minute. So this is a rate that a substance in milligrams is moving through per minute, is getting filtered into the nephron. We say, all right, well, to calculate that, it's directly proportional to the plasma concentration. So whatever the plasma concentration was of that substance in milligrams per milliliter, multiply that by the GFR. And the GFR, as we talked about in the previous lecture, is the amount of filtrate that ends up in the nephron every minute, so in mils per minute. So it's the volume that's getting in every minute. Okay, and typically on average that's going to be somewhere between 100 and 125 milliliters per minute. And so if you do that calculation, you'll notice the milliliters are going to cancel out and you end up with milligrams per minute. And so, for example, if we took a substance or a solute like glucose that gets filtered into the nephron, you say, all right, well, let's say I had 400 milligrams per ml, per 100 ml, we'll say. So 400 milligrams per 100 ml. Let me draw that here so I think it'll be a little easier for you to visualize. Let's say I took glucose and we just said 400 milligrams per 100 ml times the GFR. To make it easy math, we'll say 100 mLs per minute. And you can see that the 100 mLs cancel out and we end up with 400 milligrams per minute. So what that's saying is that, all right, if the person's GFR is 100 mils per minute and they had that much, glucose in their blood, and saying, all right, well, how much of that gets filtered every minute into the nephron? You'd say 400 milligrams per minute is filtered in there. So that's the rate the substance is filtered into the nephron. So it's entered in now. Excretion quantity. So now we're going to look at the opposite end of that nephron where the urine is being produced. And so in this case, it's the same formula and ultimately the same relationships that's going on here, only now we're looking at urine concentration and we're looking at the rate of urine production. So instead of a GFR, we're looking at urine rate. Instead of plasma concentration, we're looking at urine concentration. And same units, and you can see the excretion quantities in milligrams per minute as well. And so that's going to measure the rate that the substance is excreted. Okay. Now the filtered rate and the excreted rate, if we know both of those, that's going to help us to compare what happens to a particular substance once it's filtered. So if we're talking about glucose, as was my example, if I know the filtered quantity and I can measure the excreted quantity, I can tell you what happened to that substance while it was in the nephron in terms of whether or not some of it got reabsorbed and put back into the blood or if some of it got secreted in. So for example, if let's say I had 50 milligrams per minute of substance X, solute X, whatever it happens to be. It's filtered, and that's how much got filtered in. And 25 milligrams per minute of substance X was excreted. All right, so 50 was filtered in, 25 was excreted. Then we could say, all right, well, there's actually less substance in the urine than what got filtered in initially. So what happened to that substance? And so you could surmise that, well, 25 milligrams of that was reabsorbed. Right? Because if it wasn't reabsorbed, all right, it would have stayed in the nephron and it could have been 50 milligrams being filtered in and then 50 milligrams ended up in the urine. But instead, we only ended up with about half of that. So half of that must have been reabsorbed. So this is how we compare how it got filtered, how much was filtered, how much was excreted, and we compare the two. Now you could also imagine that if something got secreted into the nephron, so we only filter 50 milligrams per minute. But then then the peritubular capillaries, remember those capillaries that surround the nephron, maybe they start to secrete, all right? They start to secrete more glucose or more substance X into that nephron. What ends up happening is you're going to end up with, a larger amount in the urine. So for example, let's say I filter 50 milligrams per minute in this case. But what ended up being excreted was 60 milligrams per minute. It's higher than it was than the amount that got filtered, which means something must have been added to the nephron so it could excrete more. And so we call that this. We would say in this case, substance was secreted. Something must have been added to the nephron to make the urine output higher than what was originally filtered. So we're going to look at this in terms of the graphical relationship here. So let's talk about that filtered quantity again. So we're just looking at it in terms of filtration. Now, if we look at the filtered, again, the formula that we just spoke about, all right, the rate of a filtered substance in milligrams per minute, you need to know the plasma concentration and the GFR. All right, so knowing those two, that they're directly proportional to the quantity that's filtered every minute. So if you know in terms of direct proportionality here, you know that if I kept the GFR the same and I just increased the plasma concentration, well, the filtered quantity is going to increase. And the same goes for if I just increase the GFR and I keep the plasma concentration the same, the filtered quantity is going to increase and so on. So that's what we mean by directly proportional. And that's what this graph is showing. It's just saying here that you'll notice that let's say 100 mLs per minute, that's the GFR. And let's take the plasma concentration, which is down here, and we'll say it's 100 milligrams per 100 ml of whatever that substance is. So if I say 100 milligrams per 100 ml is my concentration times the GFR, which is 100 mLs per minute. And again, you can see these milliliters cancel out. We end up with 100 milligrams per minute is our filtered quantity. So let's take a look at over here, our filtered quantities over here. So that's right here, and you can see that's where I came up with this first point right here. Okay. And you could do that same calculation for all the concentrations as long as you're keeping the GFR the same. You will see that there's a linear relationship and it continues to rise. So in other words, if the GFR is held constant, which it is in this case, and I just keep increasing the concentration, the amount that gets filtered into the nephron increases linearly, just like that. So it's simple enough. It's just graphically showing you that proportionality that I spoke of. Now, if I cut the GFR in half, let's say I made the GFR 50 instead, and I incrementally increase the same concentrations over time, you'll see that the slope is decreased because I'm working with a smaller GFR. And so for every concentration, you'll see that the filtered quantity is a little bit less. But it also has a linear relationship. And same goes for if I increase the GFR to say 125, then it would have an increased slope, something like that. Okay, where again, if I increase the GFR and I continually increase the plasma concentrations, you're going to see the filtered quantity go up and up and up. So in summary, essentially, for a given GFR, let's say 100, the higher the plasma concentration, the more I'm going to filter, the higher the quantity I'm going to filter every minute of that particular substance. Now, remember, some of that substances, once it gets filtered, now I can maybe reabsorb it or secrete it. Okay, so this is the job of the nephron, the tubules, the proximal convoluted tubule, the loop of Henle, the distal convoluted tubule, the collecting ducts, and so on. Their job is then to either reabsorb this particular substance or secrete it. And in general, and it's a rule we need to remember, in general, substances that are secreted are not reabsorbed, and substances that are reabsorbed are not secreted. This is a general rule. It doesn't apply to everything. There'll be some key examples where that doesn't occur, but for the most part, this general rule does apply to most substances. So let's talk about a substance that can be reabsorbed. Okay, so we'll talk about reabsorption. So you'll notice the axes are the same, plasma concentration and filtered quantity, and so here's our filtered quantity line, which is really just representative of our GFR here, which we saw in the previous graph. And so I'm going to tell you here, we're going to assume the GFR is 100 mLs per minute. And so you can calculate the filtered quantity based on what we just talked about in the previous slide. You'll see it has that linear relationship. So it doesn't matter as the GFR is fixed, and we keep increasing that plasma concentration, the filtered quantity increases linearly as well. Now let's say we're talking about glucose. So I'm going to put glucose up here. Sorry for my handwriting. All right, glucose. Now, the property of glucose is that it will get filtered. It does get filtered into the nephron, but once filtered, it can be reabsorbed. We can take it out of the nephron and move it back into the capillaries, all right, back into our blood. And so there's another number we need to know, and that number is this TM right here. So TM is the transport maximum, all right, in milligrams per minute. And this is of substances that are to be, in this case, we're going to say to be reabsorbed, since we're talking about reabsorption. We're talking about secretion right now. But it's the transport maximum to which we can remove that substance from the nephron and put it back into the blood. So in other words, glucose, when it gets filtered into the nephron, all right, we can actually take that out of the nephron and reabsorb back into our blood. And so the cells that line the nephron, they're going to have specialized facilitated receptors. All right, and facilitation, all right, which basically means it has to recognize the glucose, bind to it, and transport it inside the cells that line the nephron, and transport it out of those cells and back into the blood. And these facilitated transporters, what they do is they have what they call a transport maximum. Right? They can saturate. There's only so much they can move over time. And so what I'm telling you now is that this TM, or this transport maximum, this means that it can only move 375 milligrams per minute out of the nephron. All right? So 375 is actually pretty close to glucoses, which is why I'm using glucose as the example here. So it's saying that this can only move 375 milligrams of glucose every minute out of the nephron. All right. So let's try a number example. So let's say I filter glucose in, and my plasma concentration, we'll use this number here, which is 200. Let's say my plasma concentration of glucose is 200 milligrams per 100 ml. Okay? And my GFR is 100. You can calculate the filtered quantity, and if you do that, you're going to end up with right around here, which is 200 milligrams per minute being filtered in. So there's 200 milligrams that get filtered into the nephron. Of that 200 milligrams, how much of that can I reabsorb? Well, my transport maximum is 375. So if it's 200, if it's underneath my transport maximum, then I'm going to reabsorb all of it. It's going to be easy enough for me to transport all that glucose out of the nephron and put it back into the body, or back into the blood. And so, this is well under. And so at this point, how much am I excreting? Well, my excretion is 0 at this point because I'm reabsorbing all of it. I'm underneath the transport maximum, so I can easily move all that back out of the nephron and back into the blood. What if, on the other hand, let's go to 500. So I'll circle this point here. If I had 500 milligrams per 100 ml, okay, and again, if I want to calculate the filtered quantity, multiply that by my GFR, and that's going to give me, again, because it's linear relationship, I'm going to filter into the nephron 500 milligrams per minute. So now 500 milligrams every minute is entering into the nephron. How much of that can I reabsorb? Well, I can only reabsorb 375 milligrams per minute of that. So of that 500, I can only get 375 back in the body because I'm beyond the transport maximum now. So that's where this green line here, reabsorbed, you see it plateaus. So the reabsorption and the filtered line are actually the same up until you see it starts to plateau right here. That plateau is because that's where the transport maximum is. So if you look back over the line over here, it's approximately 375 milligrams per minute. That's where it plateaus. In other words, I've exceeded the transport maximum capacity. So it will reabsorb 375 milligrams every minute, but it's going to leave behind 125 because remember, I filtered 500. So I filter 500, I can reabsorb 375. So how much is going to be left behind is going to be about 125 milligrams per minute. So what happens to that 125 that got left behind? Well, there's nowhere else for me to reabsorb that, and so it's going to be excreted. And so if I subtract 500 from 375, I'm going to end up with approximately, I'm going to put a little dot about right here, see right there, about 125. So you notice that excretion is going up now because as soon as you surpass the transport maximum of 375, even if it's 376, 377, 380, and so on, whatever gets left behind is going to get excreted. And so that's why you see the excretion line now increasing at that point. All right, at the point where we reach our 375, you start to see excretion going up. So the difference really between how much gets filtered, all right, how much gets excreted. The difference will always be 375 between the filtered line and the excretion line, because 375 will always get reabsorbed. Whatever's left behind will get excreted. And again, at the bottom there you can see the formula: quantity reabsorbed, filtered minus the excreted. That was like the example I gave in the previous slide, where I said if I had 50 milligrams of a substance that got filtered in and 25 milligrams ended up being excreted, we would assume, yeah, 25 milligrams probably got reabsorbed. So it's the same logic. So here, hopefully I can kind of help you understand it a little bit better visually. We're still talking about the reabsorption, so I'm just trying to show it to you visually instead of graphically. So let me just explain some of these numbers first off. This is things that you should hopefully recognize from the previous lecture, but this is the renal plasma flow, which is equal to 600 mils per minute. I calculated that for you guys from before, just a real quick reminder. The kidneys get 22% of the cardiac output, so if that's 5 liters, 22% of that. And then if we subtract off the cellular components, we get the plasma component. And the plasma component is in total to both kidneys, the total amount is 600 mils per minute. So that's how much is reaching the kidneys. Of that 600, some of it's going to get filtered in. Typically, 20% or less of it is going to get filtered into the nephron. So that's what you're seeing occurring right here. There's filtration of about 100 mils per minute. So that's the GFR. The rest of it is going to enter over here, which you can see. And I've only drawn this as a linear vessel here, but this is the peritubular capillary. I mean, I drew it as one capillary, but it would be many capillaries that, is intimately associated with those nephron tubules and kind of intertwined around it, but I drew it as just a single one to make it a little bit easier to look at. So 100 goes into the nephron, and 500 mils per minute goes into the peritubular capillaries, and that's a standard distribution. So we were talking about, let's say glucose, right? And I said, all right, well, the plasma concentration is 400 milligrams per 400 ml. So 400 milligrams per 100 ml times the GFR, which is 100 mils per minute. The mils cancel out, and I end up with a filtered quantity of about 400 milligrams per minute. And so 400 milligrams per minute is being filtered in. So that's where you get this. That's where I got this number from. 400 milligrams per minute. That's the filtered quantity. These little green circles, all right, they represent the transporters, those facilitated transporters in the cells that line the proximal convoluted tubule here. So this is the PCT. This is where glucose gets reabsorbed normally. And so the transport maximum for those cells is 375 milligrams per minute. So in this example, if 400 milligrams gets filtered into the nephron, and I can only transport 375 every minute out, that means I'm going to be leaving behind 25 milligrams per minute, which is going to go through the rest of the nephron untouched because we can't reabsorb it anywhere else. And it's ultimately going to end up in the urine as 25 milligrams per minute, which is going to be what's excreted. Okay? So again, if we compare what initially got filtered in, which was 400 milligrams per minute, and what got excreted, which is 25 milligrams per minute, you could deduce that reabsorption occurred and 375 of it got reabsorbed. All right, so this is when we compare filtered versus excreted. All right, so now I want to talk about a substance that's secreted. Just a reminder again, if it's secreted, it's not going to be reabsorbed in general. So this means, in sort of plain terms, that there's going to be something that's filtered in, and whatever gets filtered in will ultimately get excreted because we're not reabsorbing it. But it doesn't stop there, because there's going to be an extra amount that's also being excreted, and that extra amount comes from what was secreted in. When we say secreted, again, that's going to come from the blood, the capillaries that surround the nephron, and the nephron cells are going to transport this substance across and into the lumen of that nephron. And so just because it didn't get filtered in initially on that first pass, as it's in the capillaries that surround the nephron tubules, it's going to pass that substance to these cells so they can transport it into the nephron. So we're going to be essentially adding more substance to the nephron to be excreted. So So what got filtered will stay there and it'll get excreted, and we're going to add more of that substance as it goes along. So it's going to be an increase over what was filtered. So as an example, here is plasma concentration is, let's say here 10, we'll use 10 milligrams per 100 ml. And our GFR, we're going to assume a GFR of about 100. So 100 milliliters per minute. So I want to know the filtered quantity, right? To solve this, that's going to be equal to 10 milligrams per minute. And if you take a look at the filtered line here, this is, that coincides with about 10 approximately, right? So that's our filtered quantity. That's that linear relationship that we've talked about already. So that's how much got filtered, and that substance is not being reabsorbed, so 10 milligrams will definitely end up in the urine and be excreted. But that's not the total amount that's going to be excreted, because we're going to add more, and that's what secretions, that's what the secretion is all about. So there's a few other values we need to know. So I'm going to tell you that there's a transport maximum. So again, we're dealing with a transport maximum of 80. Now, when we talk about transport maximum, that doesn't only apply to reabsorption, it also applies to secretion. So if I have a particular solute and I want to move it into the nephron, all right, then it's going to, again, be some sort of facilitated diffusion or some sort of carrier that's going to have some sort of saturation kinetics. And so this can only move, this particular example, I can only move this substance into the lumen of the nephron at about 80 milligrams per minute. So that's its TM. So the question is, though, well, how much substance am I moving from the capillaries and moving it into the nephron via this pathway? Right? So I know what's filtered. I can already calculate that. I need to know how much is going from the blood and into my nephron. All right. So in order to do that, I have to know the renal, how much plasma is in the peritubular capillaries. So this is going to bring us back to what I was talking about in the previous slide. This is renal plasma flow. If you recall, under standard conditions, that's going to be about 600 mLs per minute in total going to the nephrons. Now, 100 of that is going to go inside the nephron, and that's our GFR. What's left is, if I've used 100, if 100 of it goes into the nephron, that leaves 500 that's going to enter into what we call the peritubular capillaries. So that's going to be the total amount of plasma in the peritubular capillaries. Now, I need to know this volume because I have to do another calculation. In other words, I need to know the total amount of substance that's in the peritubular capillaries every minute. So in order to do that, it's the same calculation for filtered, which I just did up here. All right, this is the filtered quantity. So this is what was filtered. So that's how much made it into the nephron directly. But now I want to know how much is in the peritubular capillaries. Well, the concentration is going to be the same, 10 milligrams per 100 ml. Concentration doesn't change, even though 100 mLs per minute went into the nephron and 500 went into the peritubular capillaries. That doesn't change the concentration at all. So it's still this. I'm going to multiply it now, but instead of multiplying it by the amount or the volume that went into the nephron, I'm going to multiply it by the volume that went into the peritubular capillaries. So in this case, that's going to be 500 mLs per minute. All right. And now again, the mLs are going to cancel out, but this is going to be reduced to 5. 10 times 5, that's going to be 50. This is going to be 50 milligrams per minute. And now this is, 50 milligrams per minute is the amount of substance moving every minute through the peritubular plasma, or through those peritubular capillaries. It's a greater amount because there's a greater amount of volume there, okay, as opposed to what got filtered in. So there's a greater amount of that substance. So now I know that I have 10 milligrams per minute that has moved into the nephron, and I know there's 50 milligrams per minute moving through the capillaries that surround the nephron. Now the question is, how much of that 50 milligrams that's in the capillaries can be moved into the nephron now? How much of that can be transported in or secreted into the nephron? Well, that's where the TM comes into play. You say, all right, well, my transport maximum is 80 milligrams per minute. This means that I can move a substance from those capillaries and move it into the nephron lumen at 80 milligrams per minute. I have 50 milligrams per minute moving through the capillaries right now. This is under the transport maximum. which means I can move all 50 milligrams per minute from the capillaries and put it into the lumen of the nephron. So therefore, I'm going to be not only filtering 10 milligrams per minute from what was filtered, plus I'm secreting another 50 milligrams per minute for a grand total of 60 milligrams per minute in my nephron now, because I've secreted 50 and I already had 10 to start with from the filtration. So it's a total of 60 milligrams per minute. So let's look back at the graph here. We calculated what was filtered, what was 10. How much was secreted was 50. So you see on the secreted, the green line here, that's 50. That's right at this point right here. So that's approximately 50. In total, how much that's going to end up in the urine? Since none of this is going to get reabsorbed, 50 plus 10 is going to be 60. So that's where you see this dot right here on the secreted line is 60. So that's how much is getting excreted. So again, we just needed to know how much of that substance was flowing through the capillary. So I'm doing the same calculation I did for the filtered quantity. I want to do it for the peritubular plasma quantity. And so in this example, at the bottom, the quantity secreted, all right, is the excreted quantity. So if I see what's in the urine, I see in the urine there is 60 milligrams per minute. All right, and I know that I've filtered 10 milligrams per minute, which means I must have secreted 50 milligrams per minute. Again, I'm just trying to show you visually what I just went through graphically to help maybe some of those who are more visual learners. But I'm using the same numbers of renal plasma flow, 600. Again, 100 is my GFR. Here's 500 that went into the peritubular capillary, so that's how the volumes have dispersed. This is the concentration I used in the previous example, 10 milligrams per 100 ml. I can calculate that filtered quantity by multiplying it by the GFR, which we did, so that was 10 milligrams per minute. That's what got filtered in, was 10 milligrams. Then we had to do the calculation. I said there's 500 mLs out here now in the peritubular capillaries. The concentration is the same. That doesn't change. Just because the volumes, took a different pathways, 100 went into the nephron and 500 went into the peritubular capillaries, doesn't alter the concentration at all. So the concentration is the same. I multiply the concentration times 500 mLs per minute instead, and I get 50 milligrams per minute that's moving through the peritubular capillaries. Now these little circles represent those transporters that can operate at a transport maximum of 80 milligrams per minute. So since 50 milligrams per minute is less than 80 milligrams per minute, it's under its maximum, it can move all 50, into the lumen of that nephron. So 10 that got filtered plus the 50 that was added every minute is a grand total of 60 milligrams per minute that ends up being excreted into the urine. And again, if you compare, if you were just to measure what happened in the urine and how much got filtered, you say, all right, well, 60 milligrams per minute ended up in the urine. I know that 10 milligrams per minute got filtered. So then 50 milligrams must have been secreted into the nephron. And finally, if a substance, all right, is neither reabsorbed nor secreted, okay, so in other words, it gets filtered, and whatever gets filtered is going to end up excreted because nothing else happens to it. Once it gets filtered in, it doesn't get reabsorbed, doesn't get secreted. So that's why you see down here, reabsorbed and secreted, it's always going to be 0. Whatever gets filtered will get excreted, and this makes it the simplest of all, of course, because it's just a linear line. It means whatever gets filtered in is going to get excreted. All right, and so it would follow this slope if the GFR, if we assume the GFR is 100. Obviously, if the GFR goes up or down, the line would change slope accordingly, as we discussed. Okay, so now I want to talk about this concept called renal clearance. So by definition, this is the rate with which a substance is cleared from the blood. So we're looking at this as taking solute out of the blood and keeping the blood in the body, ultimately. So for example, imagine I have a beaker here, and I fill that up with 100 mLs of blood. All right, and I'm going to put those 3 circles represent some solute. All right, some solute that's dissolved in the blood. Now remember, in the kidney, it's going to take in a certain volume every minute. All right, let's say that was 100 mLs per minute, which is pretty close to the GFR, right? So 100 mLs. And let's say it takes that substance and it completely gets rid of that substance. Whatever got filtered in is going to excrete into the urine. And it's going to reabsorb that 100 mLs of blood and put it back into our vasculature. So let's redraw the beaker over here, 100 mLs. And now there's no longer any solutes, and this blood has been ultimately returned to our arterioles. So what I've effectively done is I've removed the solutes from the blood and returned the blood, and the solute will end up in the urine. And so this is what we're really talking about when we talk about clearance. All right, it's the volume of plasma from which a substance has been removed in a given time, because blood is continually moving through the kidney, so it's actually a rate. It's not just a one beaker of blood here and I remove some solute. So this is going to be continually going through the kidney and filtering into the nephron, and it comes in at a certain rate. So for example, if the GFR is 100 mLs per minute, that's the rate with which blood is, or plasma is moving into the nephrons. And then let's say I remove the substance from that 100 mLs every minute and return that 100 mLs back to the arterioles, and I get rid of the substance in the urine. I'm clearing 100 mLs every minute, right? That's how this is. And we're basically looking at this because we want to know how much volume was cleared of a substance, because that actually helps us to determine the effectiveness with which a kidney can excrete substances. How readily can it clear the blood of a substance? At the same time, we can actually use clearance, the value of clearance of these substances, to actually quantify things like the volume of renal blood flow, the volume of the GFR, for example. And in addition to those things, we can actually use it to figure out if a substance, based on its clearance, is being secreted or reabsorbed by the kidney. So we can use clearance for multiple things. Again, sort of telling us the nature of that substance and how it's treated by the kidney in terms of secretion or absorption. But it also gives us an idea of volumes that have been cleared. And again, when it comes to the effectiveness of the kidney, if we're given a drug and it's cleared very readily, what that's really saying is that we're excreting that particular drug or the metabolites of that drug very easily, and we're clearing or removing it from the blood plasma and doing it at a, effectively a higher rate over time. So we can get rid of that substance or clear it from the body. Now, in order to make this calculation, all right, we need to know this formula. So clearance is in mils per minute, because again, it's a rate, as we're talking about a volume that's being cleared every minute. Okay, and it equals the urine concentration times the urine volume, or the rate of urine production. And you might recognize that formula of urine concentration times the urine volume, because we talked about it on the earlier slides. And that represents the rate of excretion, or the rate of removal of a particular substance if we're looking at a particular substance. All right, and that would be over the plasma concentration, so that gives us a ratio. So the way to kind of interpret this formula is to say, all right, well, let's say I have substance X, whatever substance happens to be, and it has a certain concentration in the urine, and if I multiply that by the urine volume, I'm going to get the rate of excretion of that substance, right? And that would be in these units of milligrams per minute, right? Because the milliliters here would cancel out. So in the numerator, you'd end up with something with milligrams per minute telling you the amount of substance that is being excreted every minute. Okay. Now, just looking at the numerator, if that were to, say be very high relative to the concentration, you'd have a higher clearance. In other words, you're excreting this, a large amount of this substance every minute, so you're effectively clearing it from the body, or in other words, you're clearing it from the blood plasma. Again, we're dealing with a volume over here, mils per minute, so you're clearing it from the blood plasma. So the higher that numerator goes, it's directly proportional to the clearance, the greater the clearance, because we're getting rid of that particular solute, and so that means there's going to be more plasma that is free of that substance. Now it's a ratio, so the bottom is the plasma concentration, so we want to compare it to how high of a concentration is actually in the blood. And so what the ratio tells us is that I might be excreting a certain amount of the substance in the urine and clearing it from the body, but if I still have a very high concentration in the blood, in other words, if this is still quite elevated relative to my numerator, my clearance is very little. what that really just means is that if I still have a very large concentration of this particular substance in my blood, despite maybe removing some of it, I'm really not clearing all that much volume, right? Because I still have lots of it still in my plasma. So that's why it's in the denominator. That's why this is an inverse relationship. The higher the concentration in my blood, the less has been cleared, because I don't have any really volume free of this particular substance. So again, reminding this is basically looking at the volume that has been cleared of a particular substance. So if the numerator goes up, all right, meaning that's the rate of that excretion of that substance goes up, then the clearance is going up, because I'm removing enough, a lot of it, and I'm going to be freeing up that plasma of that substance. So again, that's just the definition below that right there. All right, and I'm just reminding you here that a typical urine flow rate is about 1 milliliter per minute. Okay, so that's about 1.5 liters per day. This would be the typical urine flow rate under normal physiologic conditions, all right, for average adult, average water intake, for example. So those numbers here in the box that I'm giving you, oftentimes we're using it in terms of minute, all right. That would be this portion right here, so the urine volume. So oftentimes, when we're drinking throughout the day, the amount we'll actually excrete in terms of total volume is about 1 mil per minute. Okay, so that we can use that as sort of our standard in a lot of the examples, but to understand that can change depending on our water intake, whether we're dehydrated or we're overhydrated and so on. So as I mentioned in the first slide dealing with clearance, we can use that for multiple things. One of which I said is, if we're calculating a volume that has been cleared of a substance, that volume can sometimes represent our GFR. Right? Because remember, our GFR is a certain amount of volume over time that's being filtered into the nephron. So I can actually, depending on the substance I'm looking at, I can actually calculate that volume that gets filtered in. And so this particular substance that can accurately calculate this is known as inulin. Now, inulin is a plant polysaccharide that's injected intravenously. So we don't produce inulin. So there's a couple of features about inulin that make it an ideal candidate for us being able to calculate the GFR. First off, it's freely filtered, so it gets into the nephron, which is an important attribute. It's not secreted or reabsorbed, so that's another important thing. So once it gets filtered into the nephron does not reabsorb it and does not secrete more inulin into the nephron. So whatever inulin gets into the nephron is ultimately going to end up in the urine. Okay. So the amount that gets filtered is the amount that's going to end up in the urine. It's not toxic, and it's not metabolized, which of course is another useful feature. Now, the volume from which inulin is removed is equivalent to the filtered volume. In other words, since inulin can only be filtered in, it doesn't get reabsorbed or secreted, nothing happens to it once it's in the nephron, the volume that it comes in with, right? The volume that it comes in with is the filtered volume. So it's entering into the nephron in a filtered volume. And so it's being removed completely from the body and it's going to be excreted. So we're removing that substance and we're going to reabsorb that filtered volume. So the volume from which inulin is being removed from is the filtered volume. That filtered volume is the GFR. That is our GFR. All right, that's the volume over time that enters into our, or the volume per minute that enters into our nephrons. So in other words, the clearance of inulin equals our GFR, and it's because of the properties that it has. It's specific to these particular features. We don't make a substance in our body that is as good as inulin for calculating the GFR accurately. The closest we have is called creatinine. So the creatinine we actually do produce, and we produce that at a fairly regular rate, and that is a substance in our body that is closely resembles inulin in that it does get filtered into the nephron, but some does get secreted in. So there's a little bit of secretion. There's not much, but it's enough to kind of offset the GFR a little bit. So in that case, it's not perfect, but we do tend to use that more often than not in clinical settings. All right, so clearance of creatinine in the clinic is often used to represent our GFR. So I want to show you this visual representation of it. So this is, we're talking about inulin right now. Again, inulin, all right, it's filtered in, comes in with that filtered volume, okay? When it gets filtered in, it's not secreted and it's not reabsorbed. So nothing happens to it. So that's what you're seeing down here. So this little green arrow here, it gets filtered in, and it's accompanied by whatever the volume happens to be. Again, we're trying to figure out what the GFR is. And if you recall, in the earlier slides, I just gave you the GFR. I'll let you know what it is. But this is essentially how we would determine what that GFR is. So inulin gets filtered in, and once it's filtered in, you'll notice none of it's going to get reabsorbed, none of it's going to get secreted, and so whatever amount, whatever milligrams per minute that's come in, okay, is all going to end up being excreted. So the same amount's going to be excreted. The volume that got filtered, on the other hand, as you can see from the water here, that's being reabsorbed, that's being taken out of the nephron, and so there's very little water that's going to accompany that inulin. So we're not excreting the same volume there. So in effect, this is like what I was talking about on the first slide of clearance, where you are removing the substance from the volume. You're clearing the blood, right? You're clearing the blood plasma of inulin, and that's going to end up being excreted in the urine, and you're putting the blood plasma back into the arterioles there, and that will be, now that volume will have been cleared of inulin, that volume that inulin came in with, which is what we call the filtered volume. Okay. So now the volume of plasma filtered is nearly 100% reabsorbed. So this is why we're pretty confident of that volume, right? And so, and therefore inulin is removed or cleared of that filtered volume. So in this case, if we calculate the clearance of inulin, remember the formula, we'd have to know the formula for that, and we'd have to know what the plasma concentration was, what the urine concentration is, and what that urine volume is. We plug that into our formula, we get the clearance of inulin. Now the clearance of inulin, that volume, again, remember the units of clearance are mils per minute. So that rate, all right, that volume over time there that's being cleared would represent our GFR. Now I want to talk about a second substance. Keeping in mind that when we calculate clearance, the substance of, the clearance of the particular substance we're talking about matters, because the properties of that substance and how they're handled by the nephron can tell us about the volume it's been cleared from. So that's why when I talked about inulin and creatinine, which is a little less accurate, but we can use inulin and creatinine, the volume from which that's removed from is the GFR, because the properties of those two is essentially that they are not reabsorbed or secreted. If they become reabsorbed or secreted, that changes the volume from which it's being removed from. So the example I want to give now is the clearance of something called PAH, or para-aminohippuric acid. Now this particular substance has properties that allow us to actually reduce the renal plasma flow, otherwise known as that RPF. And this is talking about the total renal plasma flow. I've been using that, again, in the early examples in this lecture, at about 600 mils per minute under standard conditions, okay? So the renal plasma flow, remember, this is going to be not only the entire plasma that's in the peritubular capillaries, but also the plasma that got filtered in. So the total of the filtrate, which is the GFR volume, plus the volume in the peritubular capillaries is going to be our total renal plasma flow. And so we can actually use this molecule to help us calculate that volume. So you can see here pH is filtered in. All right. Now, in terms of its properties, it is not reabsorbed. So whatever gets filtered in is not going to be leaving that nephron. So whatever that particular amount is will end up in the urine and be excreted and be removed from the body. Now, PAH, on the other hand, what doesn't get filtered in, whatever amount doesn't, okay, can still be added to the nephron via secretion, like the examples we talked about earlier in the lecture, and it will need a transporter in order to do that. And the transport maximum for that is 80. So 80 milligrams per minute. This is actually the example I used earlier on, and I used it because it applies to this particular molecule. So what that means, again, is that if pH gets filtered in, it's not leaving the nephron. But in the peritubular capillaries, I can still add that to the nephron. So I'm adding more PAH to the pH that's already there. So that's going to also be ultimately excreted, okay, end up in the urine. So I'm removing PAH from two volumes here. The two volumes I'm talking about are the filtered volume, filtered, okay, that's what's coming into the nephron, that volume that comes into the nephron, and the volume that ends up in the peritubular capillaries, the peritubular capillary volume. So I'm going to completely remove it from the filtered volume because it doesn't get reabsorbed, and I'm going to reabsorb all that volume. And the peritubular capillary, all right, I'm going to remove it from the peritubular capillaries by secreting it in, and as long as it's underneath that transport maximum, I can transport all of it into the nephron and completely remove it from the peritubular capillaries. And it'll all end up in the urine. So effectively what I'm doing is I'm removing it from the filtered volume and I'm removing it from the peritubular capillary volume. And both of those volumes together make up our total renal plasma flow. So I have effectively cleared this substance completely, right? I've completely cleared it from the both volumes, both the filtered and the peritubular capillary volumes. And so those two volumes combined make up my total renal plasma flow. So I know the clearance of PAH equals my renal plasma flow. And finally, if I have a substance that's reabsorbed, and I don't give you a specific one right here because we don't have a particular molecule that we use for this particular situation in terms of figuring out a particular volume of our kidney. What I mean is that we have Inulin and Creatinine, which can help us calculate a GFR, and we have PAH, which can help us calculate the total renal plasma flow, and it's based on the properties of those substances. Now, of course, the flip side to that is if I have a substance that's only reabsorbed. If I have a substance that's only reabsorbed, then what I can say is that the clearance is less than the GFR. So I'll explain that. What that means is whatever that substance that gets filtered in, and we'll just call it substance X, doesn't actually matter right now, but that substance gets in and it can be reabsorbed and it's not secreted, okay? Remembering that whatever is reabsorbed is typically not secreted and vice versa. So whatever gets filtered in, I can remove some of that from the filtered volume and put it back into my renal plasma flow here, into my peritubular capillaries over here with substance, sorry for my handwriting, all right, but substance X can be removed, so that's what this arrow is indicating. So again, that's going to need a transporter, that's going to have a transport maximum as well, like the examples we gave. But I'm effectively taking that substance, it's not going to end up in the urine. In fact, I'm going to have less total substance end up in the urine because I'm taking it out of the nephron and putting it back into the blood. So therefore, I'm not really clearing as much plasma anymore. So the filtered volume, the volume it came in with in the nephron, it's going to follow some of that volume back into my peritubular capillaries. Because remember, I'll reabsorb most of that volume under normal circumstances, and I'm going to reabsorb some of that substance as well. Some of that substance may end up in the urine, so I'll have less total substance, and so some of it may end up being excreted. But the key here is that I didn't totally clear that filtered volume because some of it accompanied that volume back into the peritubular capillaries. So therefore, I'm clearing some volume, but it's going to be less than the GFR, or in other words, less than that filtered volume. So I didn't entirely clear the GFR. So that sort of kind of is a foreshadowing of how we can use clearance to help us predict how a substance behaves by comparing it to the GFR. So I'll come back to that in a minute. But if you look here, if a substance was reabsorbed, then its clearance will be less than the GFR as I just explained in the drawing. An example of that, since I didn't give you a specific example, would be something like glucose. So we know glucose is 100% absorbed in the proximal convoluted tubule, and none of it ends up in the urine. So under those normal circumstances, the clearance of glucose is 0. In other words, we're not removing it from the blood at all. All right, there's no volume that gets cleared of this particular substance. Okay, and this graph over here is what's trying to show you that. So this is the plasma concentration if we're just looking at glucose for now. At very low concentrations, which would be sort of our normal, their clearance here would be 0. We're not clearing it because it's remaining inside the blood plasma. None of the glucose is being removed from it at all. But if we were to continue to add more and more glucose, what will happen is that we would actually exceed the transport maximum for glucose to be able to be reabsorbed, and some of it would end up going into the urine, which means we're clearing some of that excess glucose from that filtered volume. Remember, that's still going to be less than the GFR though, because we're still reabsorbing glucose, and that's going to follow some of that filtered volume back into the blood. So what ends up happening is we can only filter less than the GFR, and as you can see here, no matter how high the concentration of glucose goes, we'll always reabsorb some. So therefore, we're not completely clearing that filtered volume, and so glucose here, the green line, never quite meets the GFR. Remember, the inulin line right here represents the GFR because of its properties. So you notice that it comes close, but we'll never actually reach it. Now, if a substance was secreted, then its clearance will be greater than the GFR. And hopefully that makes sense based on the example I gave, because if it's secreted, remember, it's not going to be reabsorbed then, so therefore, like PAH is the example, whatever gets filtered in will get removed. So it's going to be completely removed from the filtered volume, so it at least equals the GFR at that point. But then I'm also secreting it from that peritubular capillaries into the nephron, and also removing it from the peritubular capillary volume as well. So I'm removing it from the filtered and from the capillary volume, and together with PAH, that represents our total renal plasma flow. If it were another substance that also gets secreted in, it may not behave exactly like PAH, but the fact that we're removing it from not only the filtered but also from the peritubular capillaries means that we're removing it from 2 volumes there, which is going to be larger than the filtered volume. So that would be our GFR. In this example, the red line, okay, is PAH, and you can see at very low, so over here, down here, you can see that at very low concentrations of PAH, we would be underneath the transport maximum, being able to move that into the nephron, so we can completely remove it from that peritubular capillary. And so therefore the clearance is very high, because we can completely get it out of there, put it into the nephron and excrete it. And so it's definitely going to be higher than the GFR, which is the black line in the middle there. As the concentration of pH go up and exceed the transport maximum, we're leaving behind more and more pH in the peritubular capillaries, and so you can see that the clearance becomes less and less because we're not fully clearing anymore, and it comes close to the GFR, and it's still going to be slightly greater than the GFR because, again, whatever gets filtered in will get removed, so it's going to equal the GFR there, and whatever we remove from the peritubular capillaries will also be added volume, all right, that it's being removed from, even if it doesn't totally remove the entire quantity from that from the peritubular capillaries. So, if a substance is so highly secreted that it entirely removed from the plasma, then the clearance equals the plasma flow, right? And so that's what pH does. pH is administered intravenously. Again, we don't produce that endogenously. pH is used to measure that renal plasma flow. And we can take that renal plasma flow and we can convert it. If we know what the hematocrit is, we can convert plasma, the plasma flow there, and we can figure out what the total or whole blood volume is too. You just have to divide it by 1 minus whatever their hematocrit is. And that'll tell you the whole blood volume. So I said earlier that clearance is a measure of how the kidney handles a specific substance. Right? And so we can use clearance to predict, if something is secreted or absorbed, as long as we know the GFR. Okay. Now, there's a couple things in terms of the substance that the clearance is going to depend on. So, for example, whether or not that substance is filtered in the first place. All right. If it's secreted or reabsorbed, so what are those properties? The plasma concentration of it, and of course the transport maximums for this particular substance if it's being secreted or reabsorbed. So these would all come into play in how the kidney is clearing it. And so hopefully that makes sense, because if we're trying to, say, reabsorb something, and we have a very high plasma concentration of it, we may exceed that transport maximum. So that's going to change the clearance values. All right, but ultimately, even though it may change the total clearances, if we know the GFR, if it's being secreted, we already know that it's going to be greater than the GFR. If it's being reabsorbed, it's going to be less than the GFR. And we can use that information. But we just have to remember, so these are the keys, we have to remember that to determine the GFR, we have to have the clearance of inulin or creatinine. And so we now know what the GFR is, so we'll have a baseline. The renal plasma flow, so we can figure out what the total volume of plasma is that's going to the kidney, or the kidneys, and that's PAH. So they play that critical role because of their properties. And since we give inulin and PAH IV, we can control the plasma concentration so that we make sure that it's very accurate. Now, in terms of comparing those substances, we're going to use a ratio. All right, so we're going to compare the comparison of a substance to the clearance of inulin. So remember, we need to know what that GFR is for our baseline. So then we can make a comparison. Is it greater than the GFR or is it less than the GFR? So here's our ratio. The clearance of whatever substance X, so the clearance of X over the clearance of inulin, or in some cases creatinine, depending on what you're using. Now, if the clearance of this substance is the same as the clearance of inulin, you're going to get a ratio of 1. Right? So the two clearances are equal. So that tells you that this substance is not secreted and it's not reabsorbed because it's behaving like inulin or it's behaving like creatinine. Okay? If on the other hand you get a ratio that's greater than 1, remember, if it's greater than 1, we're removing it from not only the filtered volume, but also from the peritubular capillary volume. So it's an extra volume that we're removing it from. So therefore, this substance must be being secreted into the nephron. So whatever's getting filtered in is being removed, and we're also removing it from that peritubular capillary. So therefore, this ratio would be greater than 1. This substance, if the ratio is greater than 1, the substance is being secreted. And then lastly, and you probably know this already, if it's less than the GFR, then it's being reabsorbed because we're not removing it from the entire filtered volume anymore. Some of that's being brought back into the body. It's not being completely cleared. So that filtered volume is not being completely cleared, and so therefore it's going to be a number that's less than 1. Glucose, again, would be an example of that, where if it's 100% reabsorbed, then it's going to be 0. Okay. Now, just to give you some sort of clinical correlation, understand that creatinine and BUN are often used to look at the GFR of a patient. And we use GFR to help us assess the health of a kidney. So I told you that a GFR is typically between somewhere around 100 mils per minute up to maybe 120 or 125 mils per minute. And so that would be sort of standard healthy adult. Now, if the patient, say, has some stage of kidney disease or dysfunction, the GFR would typically go down. So in kidney disease, you might see the GFR drops to, say, 90, mils per minute, or 60 mils per minute, or 40, and so on. And so what that's suggesting is that we're getting less and less filtration, and that actually portends a worse disease, or it suggests a worse disease of the kidney, the lower it is. And we can actually essentially assess GFR function in, say, a hospitalized patient by trending creatinine and blood urea nitrogen in the blood. The reason we can do this is because both creatinine and BUN, well, they're being produced constitutively. So it's all the time they're being produced at a certain rate. And so there's a certain concentration in the blood. And what happens is they get filtered by the kidney into the nephron, and then they get excreted at a certain rate. And so there is a steady state under normal conditions where we produce creatinine and BUN at a certain level, and we excrete it at a certain level. And so when we reach a steady state, the production of it and the excretion are equal to each other. And that's when we have a steady state. Now, if, let's say, the kidneys was damaged and the GFR starts to go down, so we're not filtering, well, I can't filter as much of that BUN and creatinine into the kidney and excrete it. More of it ends up kind of getting backlogged or getting left in the blood. And so the concentrations of creatinine and BUN can elevate if the filtration goes down. This is based on like what I was talking about at the very beginning of this lecture in terms of filtration. right? The quantity filtered, it has to do with the concentration as well as that GFR. So if the GFR goes down, the quantity that's getting filtered in is going to start to go down, and it's going to accumulate in the blood. So this is why I say creatinine and BUN are inversely proportional to the GFR. As GFR goes down, the levels of creatinine and BUN in the blood go up. Okay, they're no longer in that steady state, so they'll go up until there's a new steady state. So, for example, if GFR is reduced by half, the BUN and creatinine will double in the blood. If the GFR is down by, let's say, a third of normal activity, then BUN and creatinine will triple. So this is the relationship that it has. Its tripling will create the new steady state, but we're going to have a higher steady state. Now, we can use this information to trend the GFR. If somebody, say, is hospitalized and has maybe some kidney malfunction or something we're concerned about, you can follow the BUN creatinine levels and see if they start to rise, right? That can be suggestive of kidney malfunction. So let's try an example of renal clearance, all right? So if we determine, again, renal clearance by collecting, so what I'm basically telling you here is we're going to collect, a blood sample so we can measure a concentration of a substance, and then urine sample. So both the volume that's been produced over time as well as the concentration of the substance in the urine, because those are all the variables we need to calculate a clearance. Okay, so we're going to use urea in this example. If urea concentration is in the urine, again in the urine, is 6 milligrams per mil, and the urine output is 2 mils per minute, all right, and the urea concentration in the plasma is 0.2 milligrams per ml. So I gave you all the variables you need to calculate a clearance. So remembering the formula, okay, then you can plug that in, all right, and calculate the clearance of urea. The last bit of information I give you now is also, I'm going to give you that the GFR is 100 mLs per minute. So my question is, what is the clearance of urea? All right, again, that's just plugging in the formula, but you gotta make sure you know how to interpret that. All right, and then I ask, is it reabsorbed or secreted? Well, now you have to understand how we can figure this out by knowing the GFR. So you can pause now and try it for yourself before you look at the answer, but I'm going to continue. All right, so the clearance, that's just the formula for the clearance. It would come out to about 60 mils per minute. And so how do I interpret 60 mils per minute? Well, 60 mils of blood plasma is completely cleared of urine per minute. I told you that the GFR is 100. So now I can compare the 60 mils per minute to the GFR, which is 100 mils per minute. So I can make that ratio I just talked about in the slide before, all right, or 2 slides ago. 60 over 100. So remember, this is the clearance of X, which in this case is urea, over the clearance of, we'll say, inulin. Let's say I've already calculated it for you, but the GFR essentially. 60 over 100. So this is definitely less than 1. Less than 1 means it's being reabsorbed, right? I'm clearing it from a volume that's less than the filtered volume. So that tells me that some of the urea is absorbed. And in fact, that's actually true. And I'm going to talk about that in actually the slides to come, how urea, when it enters into the nephron, will be reabsorbed in parts of the nephron. And we can utilize that for helping us to draw water back into our bodies and so on. And I'll get into the mechanisms of that later. But this is how we would interpret and use this information. Okay. So now I want to talk about, renal regulation of water balance and the extracellular fluid volume. Now this is kind of the missing piece that I didn't go into in the first 2 lectures that we had on, fluid homeostasis. I always just kind of said, we'll get to the kidney, we'll talk about that a little bit later, because I didn't want to add this piece just yet. So now I want to talk about how the kidney is going to handle the shifts or the changes in volume that we would get, all right? So in the extracellular fluid, really what's important to know for our body's sake is the osmolality, which, if you recall, is normally about 285 milliosmoles per liter. And it ranges, again, the range can be like 270 to 300, so there's a range, okay? 300 would be sort of the top end. What happens is that if if we become dehydrated, it triggers thirst mechanism in our hypothalamus, which has what we call osmoreceptors. And what that means, let's say if we're dehydrated, it means that our osmolality is going up, right? We have more solute than volume, so we're going up to, say, from 285 to 290 or 300 or 305 or whatever, but the osmolality is rising because we're losing volume, losing that fluid. So that's going to trigger the hypothalamus, all right, to increase our thirst. Then we also have antidiuretic hormone. Antidiuretic hormone, all right, also known as vasopressin because it can act on blood vessels and cause constriction, vasoconstriction. But ADH in the kidney, it plays several different roles, and all of which have to do with making sure that we can reabsorb more water. So again, in the state of dehydration, ADH levels would be elevated. They would act on the kidney, on the nephron tubules there to reabsorb that water. Okay, and it's secreted from the posterior pituitary, and we'll talk about sort of the mechanisms of that when we get to the endocrine lectures. And then in aldosterone, aldosterone is a hormone that I've mentioned before. It's part of that renin-angiotensin-aldosterone pathway. And so the kidney can release renin in response to low volume states, which will produce angiotensin 2, which can then trigger the release of aldosterone from the adrenal gland. And aldosterone levels rise, and it acts on the kidney as well. And what it does is it stimulates the reabsorption of sodium. By reabsorbing sodium, water is going to follow that sodium passively, because sodium is osmotic. And so water is going to follow that back into the body as well. So it helps us also to increase volume that way, but we're also reabsorbing sodium in the process. Okay, so what I'd like to do here is take you through the different parts of the nephron and show you how water is reabsorbed at these different parts of the nephron. So in my drawing over here, all right, this would be the proximal convoluted tubule over here. This would be the distal convoluted tubule, collecting duct, and then of course the loop of Henle. And so in the proximal convoluted tubule, 67% or 2/3 of the water is actually passively reabsorbed there. In fact, when the solutes get reabsorbed, the water follows with it because they're osmotic. So when sodium gets reabsorbed, the water comes with it. And so of the blood that gets filtered in, all right, that blood is going to be isoosmotic, all right. So the blood that was recently in the vasculature. So it's 285 milliosmoles. You start to reabsorb the solute, the water follows it in proportion. So at the end of the proximal convoluted tubule, even though we've reabsorbed 2/3 of the water, the osmolality hasn't changed because we reabsorbed solute along with it. However, now as we turn the bend and we go into that descending portion of the loop of Henle, we're descending into the medulla. You can see I've kind of delineated that by that dotted line there. So we're going to move down into the loop. So an important feature of the descending limb is that the descending limb is water permeable, but no solutes are going to be able to be reabsorbed there. So what happens now is that the water will continue to move. So again, water is leaving out over here. Water can leave from the descending limb. All right, and the reason water leaves from the descending limb without the solute is it's water permeable, and the medulla has a very high concentration of solutes. And in fact, the deeper you go into the medulla, the higher the concentration goes. And in fact, at its deepest point, that concentration is going to be about 1,200 milliosmoles. I'm going to put 1,200 out here. They would equal each other because what happens is this. As this solution, this 285 milliosmoles, goes into the loop of Henle, the solutes remain behind as the water leaves and goes into that concentrated medulla. Remembering water goes towards the higher concentration, which in this case is going to be that interstitial space in the medulla. So it's going to start to concentrate more and more as it drops down into this loop of Henle, and it loses more and more water to the medulla until there's essentially like an equilibrium with what's in the interstitium there, which is about 1,200 milliosmoles at its max. Then it's going to round the corner and go to the ascending limb. Now the amount that actually has been reabsorbed here, so if we have 67% in the proximal convoluted tubule, we're talking about 20% or so in the descending limb. All right, so that's about 87% has already been reabsorbed now. But when we get to the ascending, the important feature here is that things switch around. So while the descending limb was permeable to water and impermeable to the solute movement, it is permeable to solutes and impermeable to water. So what does that mean? Basically, water does not leave, but the solutes will. And so that, in fact, located in the membrane of these cells here, I'm just going to draw little boxes here. to represent the fact that there are transporters that are going to move solutes against its gradient, so it's going to require some energy, all right, is going to move solute into that interstitial space. And in fact, it's those transporters that keep the medulla at a very high solute concentration, because these are actively moving these solutes against their gradient into that interstitial space. So that's how we get that gradient in the first place. And this is primarily going to be sodium, 2 chlorides, and potassium. And in fact, if you take a look in this red box up to the top here, that transporter that I was just drawing, those little boxes I've drawn are right there. So this is the lumen of the nephron here. Here's the blood. So on the face of this the cell that lines the lumen there, all right, on the apical portion of it, you'll see there's a transporter that moves potassium, sodium, and 2 chlorides inside the cell. So we're removing that solute from the tube there, and so it's going to redistribute that chloride and that sodium into the interstitial space where it contributes to that high concentration. Potassium can get moved back in and ultimately get put back into the nephron and get kind of recycled, if you will. But we'll come back to potassium later. So this is essentially, we're moving the sodium chloride into that interstitial space. What does this mean? So if I'm moving solute out and leaving the water behind, I'm going to start to dilute what's in the nephron. So it's going to go from 1200, as it ascends, it's going to go to 900, 600, 300, and so on. So it gets more and more dilute because we're removing the solute and leaving the water behind. And so we also refer to this as the diluting segment. Okay, and in fact, by the time it reaches the early part of the distal convoluted tubule, it can be as dilute as 100 milliosmoles, because we'll continue even into the early distal convoluted tubule to reabsorb sodium chloride, and the early distal convoluted tubule is impermeable to water as well. So here we're just getting rid of the solute, we're reabsorbing that solute. Now, at this point, all right, so I'm going to stop there. We'll talk more about the distal convoluted tubule and the collecting duct in some of the upcoming slides. But the last point I want to make is about ADH. So I said ADH is for reabsorption of water, but at this point, just to point out that ADH augments the activity of this this receptor. So here, ADH, I'm going to put a little positive sign. It enhances its activity. So in other words, it can really dilute that diluting segment. It can move even more solutes into that medullary interstitial space there and leave behind a much more dilute solution in the nephron. So it could be, so it'll create a greater concentration gradient, which will become more important. I'll talk about that later. But that concentration gradient will become greater in the medulla, and that's going to be important for being able to reabsorb water. So since we got pretty much through the loop of Henle and into the early distal convoluted tubule, I just want to quickly again kind of talk again about this, the function of this loop of Henle, because when it dips into the medulla, that medulla again having a very high concentration in the interstitium plays a very important role. So here they're using the 300 as our milliosmoles, as our normal. That'll be the high end of normal. But this is at the end of the proximal convoluted tubule up here. So it's going into the descending portion. And you notice that the concentrations are going up all the way up to 1200 milliosmoles. You see that the water here is being reabsorbed, leaving behind the solute, and so it becomes more and more concentrated. Okay, as we round the bend here, all right, that's very salty fluid, all right, enters the ascending limb. The ascending limb's properties change. Oftentimes referred to as the thick ascending limb because the membrane there is thicker, which is why they drew it that way. You see here as it ascends, it becomes more and more dilute. The reason? Because those transporters I just talked about are removing sodium, potassium, and chloride and leaving behind the water, so it becomes more and more dilute. And this is an active process because, again, we're transporting these ions into an already very high concentrated area. And so this makes it more and more dilute. Okay? And then by the time it reaches the early distal convoluted tubule, it can be as low as, say, maybe 100 milliosmoles or so, because we're continuing even in the early distal convoluted tubule to pump that out. To pump out those solutes, that sodium and chloride particularly. Over here is just again to show you this portion down here is the renal medulla, and you'll see how the loop of Henle here dips into that renal medulla. The rest of the nephron is located actually in the cortex, but just the loop there dips in there, and it dips because it allows us to have this property of removing water and then diluting and so on. Diluting on the ascending portion. So lastly, before I move on, That ascending portion with those pumps that are moving the sodium chloride into the medullary interstitium there, they play the vital role of maintaining that high concentration of solutes in the medulla that also helps to draw out the water from the descending portion. So they work together, and we call this a countercurrent multiplier because they're both moving in separate currents, right? The descending limb and the ascending are moving in opposite directions. One's going down into the medulla and the other one's coming out. And so one limb is affecting the other. So as the ascending limb is pumping more and more ions into the interstitium, that's creating the gradient that's helping to draw water out of the descending limb. So we call that countercurrent multiplier. Now this countercurrent multiplier is seen here again. You can see in yellow the nephron. All right. Now, again, here's at the end, they're using 300 milliosmoles. This is the normal here. 300 milliosmoles of fluid here at the end of the proximal convoluted tubule as it descends into the medulla, which is the darker shade here. 400, 600, goes all the way up to 1200 again, rounds the bend and becomes more diluted. It's becoming diluted again because of these transporters. So sodium chloride, potassium are accumulating in the medulla there. So this is all the stuff I went over on the previous slides. You're just seeing it again. Okay. So again, this is the countercurrent multiplier because this is going to create that gradient that will affect the descending limb and reabsorb that water. Now, the other feature I want to point out here is the blood vessel over here. Now they're showing the blood vessel separated to make it easier to view, but understand that this Vasa recta would be closely approximated to that nephron loop. All right, they'd be intimately connected to one another, so they wouldn't be separate like this. They're just showing it separately so that we can visualize it better. So this loop would follow the loop of Henle, right? This Vasa recta, and so this is the blood, the capillaries essentially that are flowing along by this loop of Henle. This guy's job, or this Vasa recta's job, you'll notice that inside the blood there, this capillary is going to be affected by this high concentration in the interstitium as well. So as the blood moves in into the medullary region following that nephron loop, you'll notice that the concentration of solutes inside the blood gets higher and higher as water leaves, because again, water is going to move towards the higher concentration in the medulla. And the solute concentration in the blood also goes up to about 1200, and then it becomes more and more dilute because as it's concentrated, water is going to actually move back in. All right, and it'll be collected back into the nephron because as we go to higher and higher parts of the cortex, of the medulla, it's less and less concentrated relative to the blood that's coming into it as it's ascending, and so it's going to reabsorb that water and ultimately go back to its normal. All right, and it's going to give up some of that sodium chloride that it took in initially here down its gradients. So this is different effectively from what we saw in the nephron loop, because the nephron loop is permeable to water as it descends and impermeable as it ascends, and it separates solutes from each other. So solutes don't move in the descending limb, and in the ascending they're pumped out. Here in the blood though, that's following this nephron loop, water is moving out towards the higher concentration, and sodium is going to go and try to equilibrate with what's in the blood there. So we have solute moving in just as much as water is moving out. We're going to get sort of an equilibrium there. So it's picking up some of that sodium and distributing some water, and as it ascends out of the most concentrated portion of the medulla, the distribution continues. However, as it's bringing higher concentrated blood into the less concentrated medulla, as it rises out, it's going to lose some of that sodium and take back some of that water. Ultimately, the whole job of the Vasa recta is to help maintain the gradient that has been established by the nephron. Okay, so by going in there, what it's really going to do is ultimately, the idea here is that this Vasa recta is going to help remove excess water and salt that might be accumulating in the medulla. And so by removing that extra water or that extra salt, okay, it's going to help maintain the gradient or maintain the concentrations of the medulla. And so again, that's without getting into too much detail about the particular functions of those, but that's the idea. All right, that the gradient is established by the nephron loop via that ascending limb and those pumps, and that helps us to draw water out of the nephron on the descending portion. And then that extra water and solute that's being accumulated there will then be dealt with by the Vasa recta, which will take up any excess water or take up any excess salt and redistribute that back to the vasculature. And that helps to maintain that medullary concentration. All right, now ADH, I want to come back to ADH now. So a couple things about antidiuretic hormone. All right, it's again secreted by the posterior pituitary, and it goes up in response to dehydration. So dehydration, loss of this water, and the solute concentration goes up, so the osmolality would go up. So ADH goes up in response to a high osmolality. So that's why I said loss of blood volume and rising blood osmolality stimulate the hypothalamic osmoreceptors, all right, which are, being specific, are in the supraoptic nucleus, all right, and they're very sensitive to changes in osmolarity. This is going to trigger the release of ADH from the posterior pituitary. ADH, all right, makes the late distal convoluted tubule, not the early portion, which we talked about, but the late, as well as the cortical collecting duct it's connected to, and the medullary collecting duct. So I talked about the collecting duct, the part that's in the cortex and the part that's in the medulla. It makes those portions of the nephron more permeable to water. So when it acts on those cells in the late distal convoluted tubule and the collecting duct, they're going to insert aquaporins, which are going to allow water to move. Okay, so it makes them more permeable. Without ADH, they are impermeable to water. In fact, the distal convoluted tubule collecting ducts will not allow the movement of water at all, unless there's ADH present to put in those aquaporins. So, in addition, ADH also augments the sodium chloride reabsorption in the diluting segments, which I talked about, which are part of the ascending limb and the early distal convoluted tubule. And finally, water in the tubular fluid re-enters the tissue fluid and the bloodstream rather than being lost in the urine. So to put that all together, ADH, all right, can act on the ascending limb and the early distal convoluted tubule, where it augments the actions of the receptors that are moving solutes into the interstitium. That's going to help create a larger gradient in the medulla, which is going to help us reabsorb water better. Now, at the same time, ADH can also act on the late distal convoluted tubule as well as the collecting ducts. And when it acts on them, they'll insert aquaporins, and they'll go from impermeable to permeable to water. Okay, so that's what it's doing. It's making the distal convoluted tubule and the collecting ducts permeable to water and enhancing the electrolyte reabsorption in the ascending limb. So what this is going to do is it's going to set up a gradient in the medulla, help maintain that gradient in the medulla, so that water will want to move towards that higher concentration. All right. So the collecting duct, all right, this begins in the cortex. So if we're looking over here, just so you can see a visual, so you see this is the glomerulus over here, all right, proximal convoluted tubule. This is the loop of Henle, and then you see over here, this would be the distal convoluted tubule, and then this is the collecting duct in the cortex, and then the collecting duct in the medulla. The collecting duct runs through the medulla and reabsorbs water. So what happens is, if ADH is present, remember, ADH can act on both the distal convoluted tubule as well as the collecting duct and increases their permeability. So remember that this collecting duct goes through all the way through the medulla, through the deepest portion of the medulla, all right, where it ultimately becomes the renal papilla and into the calyx to be excreted as urine. So if I have a very high concentration, you see in the medulla, the concentration gets higher and higher. Now, in the presence of ADH, that's going to make the collecting duct permeable, and so water will readily leave the collecting duct and go towards the higher concentration. It'll leave the collecting duct and go into that interstitial medullary region. Okay. Now, ADH has also done work on the ascending limb of the loop of Henle. Okay, and what that's done is that's helped to create the gradient. So it augmented those receptors so that that gradient was greater, and then it also makes the collecting duct permeable so water more readily leaves. So it's working both those angles, increasing the gradient and allowing water to permeate. So this is the value of ADH in reabsorbing that water. Create the gradient and produce the channels to allow water to move in the collecting duct. And it only happens if ADH is present. Okay, if ADH is not present, then the collecting duct and the distal convoluted tubule are impermeable. Okay. Now the cell type that's specifically being activated by ADH to increase water permeability in the collecting duct and the distal convoluted tubule are called principal cells. So ADH acts on principal cells that will increase their aquaporins and allow water to move. Things that trigger ADH release: increased osmolality, we talked about, right? Part of our thirst mechanism in our pituitary, our hypothalamus, and then activating the pituitary. Angiotensin 2, we talked about, part of the renin-angiotensin-aldosterone system. So angiotensin 2 can stimulate its release, and it's a very powerful stimulator. And baroreceptors, which we've also talked about in terms of our blood pressure regulation. So baroreceptors, when they start to activate, right, if there's, say, a drop in our pressure, they fire less frequently, it increases sympathetic output. This can actually induce the release of ADH, which can help bring up that volume and help bring up that blood pressure as well. So the most prominent, those stimulators are going to be an increase in osmolality as well as the angiotensin 2. So a state of high volume, right? High volume or low osmolality, because we have too much volume relative to our site, is going to drop our osmolality to less than, let's say 285. That's going to drop our ADH levels because our volumes are high. So we're going to have low levels of ADH because we're, too much volume. So there's going to be little to no water reabsorbed in the distal convoluted tubule or the collecting duct. The reason is, remember, they're impermeable unless ADH is present. So if ADH levels have dropped, all right, theoretically, if there's no ADH, then it's impermeable. And so you're going to have very dilute urine, okay? So it produces dilute urine, and in fact, it can be as dilute as 50 milliosmoles per liter. And it won't matter the concentration in the medulla there, because if the water is impermeable, it can't flow out. So you can have very, very dilute urine, and as dilute as it can become is as much as 50 milliosmoles, or as little as 50 milliosmoles. The blood becomes more concentrated in those states, okay, because we're losing that volume now. So we can concentrate the blood and bring that osmolality back up. However, in a state of low volume, right, in a state of, say, dehydration or high osmolality, so it's greater than 285, then ADH is going to be secreted at higher and higher levels, again, depending on the state of the dehydration and so on. But ADH levels will rise. We already talked about what ADH does. So water is going to be reabsorbed from the distal convoluted tubule and the collecting duct. It's more readily absorbed because it affects those principal cells, increases aquaporins, and water can now move into that medullary interstitium, which has now this very high concentration. It also augments the production of that concentration by acting on the ascending limb and increasing the activity of those receptors. What's going to happen is in this case, the blood is diluted. Okay, so it dilutes the blood by reabsorbing more water, and the urine becomes concentrated. So we're getting rid of more solute. All right, and we're reabsorbing water and getting rid of solute, so we can dilute that blood and bring that osmolality back down again. And we can concentrate the urine up to 1200 milliosmoles because that's about as concentrated as we can make the medulla. So it can come into equilibrium with that at about 1200 milliosmoles. So our range of concentration is from 50 milliosmoles, all right, when we're trying to get rid of volume, up to 1200 milliosmoles when we're trying to reabsorb it in the state of dehydration. Okay, so to summarize some of the actions we talked about in the nephron, first off, in the proximal convoluted tubule, all right, we reabsorb about 67% and another, say, 20% in the descending limb. Now, the reason we can reabsorb in the descending limb is because on the opposite side, we have that countercurrent multiplier system, right? So this is where these receptors are reabsorbing, sodium, chloride, and potassium. And this creates a very large concentration, or very high concentration in the medulla. So I'm going to see that dotted lines, we're in the medulla here. So anything below that. So this creates a high solute concentration in the medulla, which this high concentration is critical. All right, by creating a high concentration here, which is produced by that ascending limb and maintained by the vasa recta, affects the descending limb because that's how water gets pulled out from that high concentration. And in the presence of ADH, if ADH is present, it's going to make the collecting duct and the distal convoluted tubule more permeable to water. Now, the effect on the collecting duct, of course, is by making it more permeable, it's going to be affected by this medullary concentration gradient. So it affects not only the descending limb, but it affects the collecting duct as well, as long as ADH is present for the collecting duct. And this is going to help us to reabsorb water by having that gradient there. All right, so that's the importance of these particular receptors, okay, and maintaining that medullary concentration. Now, in addition, all right, you'll notice that if you remember that the ascending limb is impermeable to water otherwise, and the early proximal convoluted tubule, or excuse me, the early distal convoluted tubule is also impermeable. All right, they're not affected by ADH at all, but the late distal convoluted tubule and the collecting ducts are affected by ADH via those principal cells, and they'll increase their permeability. Without ADH, they're impermeable as well. So in a state of dehydration, ADH goes up, it makes the collecting duct and the distal convoluted tubule permeable to water, and it turns on or increases the activity of those receptors that creates that very large gradient in the medulla that helps us draw the water out. So it works well for that. If we're in a state where we're, too much volume, ADH levels are down, and effectively the second half of the nephron here becomes impermeable, right? Without ADH, it's impermeable to water. So the distal convoluted tubule, the collecting ducts don't allow water through, even if there's a gradient in the medulla. All right, the receptors will continue to pump out, but they won't be augmented by the activity of ADH. So before I move any further with that, last thing I want to say is I'm going to draw something else here. All right, this is to signify that a loop diuretic inhibits the activity of those ascending receptors there, those sodium potassium chloride pumps. So a loop diuretic is used, all right, in certain conditions like, let's say, heart failure or so on, and it acts at the ascending limb of the loop of Henle. And considering the importance of creating that medullary gradient, a loop diuretic is very effective for getting rid of volume. All right, so say if somebody's volume overloaded in heart failure, for example, if you give them a loop diuretic and it inhibits that, I can't create or establish a high concentration in the medulla there. So what is that going to do? That's going to affect the ability to reabsorb water in the descending portion of the loop of Henle, and it's going to affect my ability to reabsorb water from the collecting duct or from the collecting duct, in the presence of ADH. So even if ADH is present, remember ADH relies on the fact that there's a gradient. So I can put the pores there, but if there's no gradients, right, water's not being drawn out into the interstitium. So the loop diuretic is very effective for getting rid of volume because it messes with the established gradient there, and it can reduce it. And the last thing I want to mention, just before I move on, is that you probably saw it in the previous slide and I actually neglected to mention, so I want to bring it up right now, is that urea. I gave you the example of clearance of urea, and I told you urea is reabsorbed. And in fact, there's something called this urea cycle here. And so urea from the collecting duct, ADH actually increases the permeability of urea. So when ADH is present, urea can move out of the collecting duct, down its concentration gradient, and into the interstitial space there. When it's in the interstitial space, it can actually re-enter the nephron in the descending loop here. So urea can enter here. And so this is sort of the cycle we're talking about. Urea enters in through the descending loop, goes up the ascending, it's impermeable to the ascending, the distal convoluted tubule, and the cortical collecting duct, and it's only permeable in the medullary collecting duct in the presence of ADH. What ends up happening is in the presence of ADH, that extra urea, the urea here adds to the osmolality of the medulla. So in fact, the last point I want to make, all right, is that the established gradient in the medulla relies on that sodium, primarily sodium, chloride, and urea. Urea is a significant contributor to the concentration that helps to pull water out of the collecting duct there in the presence of ADH. So ADH not only augments those receptors that put sodium chloride there, but it also increases the permeability of urea in the collecting duct, so urea can collect or can increase in concentration in the medulla and help to draw water out as well. And so, as I've spoken about earlier on, I told you urea is effectively, it's permeable and it can permeate easily. And yes, in some cells, like red blood cells, for example, it does move across membranes very readily. But the kidneys, these cells are very, very highly specialized. In fact, we talked about water being mostly permeable, and as you can see here in the nephron, water, all right, can be permeable or impermeable depending on the nature of the cells. And these cells, for instance, in the collecting duct and the distal convoluted tubule, are impermeable to water unless ADH is present, or impermeable to urea unless ADH is present. So they take on a different role from what we've been learning. So you'll see there are exceptions to these rules, and the kidneys have many of the exceptions because of the function that the kidney has to carry out, being able to separate, water and solutes and being able to regulate them differently. So in any case, we have this urea cycle enters here, and again, if ADH is low, right, ADH stimulates the release of urea and helps to concentrate that medulla as well. If ADH levels are low, urea is not reabsorbed and it's lost in the urine along with the extra water. Okay, to finish up, I want to talk about a concept called free water clearance, which is essentially a measure of how we can concentrate urine. And just like clearance, as I've mentioned earlier, is we're talking about how we can, how much of a volume of blood is cleared of a substance over time. Here we're talking in terms of free water clearance is how much of the blood plasma is cleared of solute-free water. So that blood plasma, how much of the water are we removing? Okay, it's kind of like treating water like it's the substance that's being removed from the plasma. Okay, and in doing that, we can kind of get an idea or a measure of how the kidney's concentrating the urine or diluting it. So, for example, it's logical in this sense. If somebody is dehydrated, if the kidneys are healthy and normal, what happens is the kidney's response is going to be to increase ADH, reabsorb the water, and in turn, that's going to concentrate the urine, right? We don't want to lose any volume. We're going to conserve it and keep that in the body, so the urine is going to be very concentrated with very little water. So you're going to have a high solute and very little water. And then the opposite is true, right? If we're in a state where we have too much volume, then with the kidneys, the ADH level is going to drop, and we're going to actually get rid of more water than we are solute, and so we're going to have a very dilute urine. And we can compare the osmolality of urine to the osmolality of our blood, for instance. So we can say, our blood is 285 milliosmoles, and the urine is 1200 milliosmoles, right? That's about as concentrated as we can make it. So it's very concentrated. So we have a lot of solute and very little water. And the kidney is able to separate the two. It's able to actually reabsorb water and get rid of solute, or get rid of water and conserve solute. So it's able to separate the two in order to adjust our osmolality. That's the whole point, right? We want to keep it at 285 milliosmoles, and that's a certain ratio of solute to water. If it's off, it can adjust it by changing the solute or the water, right? So in this case, when we talk about the clearance of water, how much of this solute-free water has been cleared, how much of the plasma has been cleared of this water. And so this is our way of looking to see if the kidneys are really kind of doing this appropriately. All right. So for instance, urine that is isoosmotic to plasma. So if the urine is 285, the plasma is 285. This can happen again depending on our state of hydration and so on. A common example of this would be, say, like the loop diuretic. So the loop diuretic, which inhibits those pumps on the ascending limb, doesn't allow us to concentrate our medulla at all, and so we lose the ability to reabsorb water and concentrate the urine, excuse me. And in doing so, what ends up happening is we end up with an isoosmotic urine. Urine that is hypoosmotic to plasma, right? So this is one that would be very dilute. We call this the clearance of water is positive. We're removing, some free water from the blood plasma, so we call it positive. And in this case, the ADH is suppressed. Okay, right, because the ADH would otherwise reabsorb it, so we're losing the water, so ADH is suppressed. This is typically due to high water intake or in disease states like diabetes insipidus, where we have abnormally low ADH levels, or the ADH levels are normal, but the kidney's not responding to it, and so it's not able to reabsorb that water, and we end up with very dilute urine, as low as maybe 50 milliosmoles, which of course is definitely hypoosmotic to our plasma. And then lastly, urine that is hyperosmotic to the plasma. So if it were 285 in the plasma and the urine is, say, 1200 milliosmoles, that would be hyperosmotic urine. And we call this the clearance of water is negative. meaning we didn't really clear the blood plasma of much water at all, of free water. And so we'll say the clearance of water is negative, and the ADH is, the ADH would be elevated in this case. So in high levels of ADH and dehydration, you'd have a very concentrated urine. It would be more hyperosmotic, and that would be normal. In some disease states, though, the ADH level might be very elevated, like SIADH. And so in SIADH, you have high levels of ADH, and so this causes lots of reabsorption and high concentrations of urine, and it can cause some volume overload issues. So anyway, in summary, that's really just sort of clinically, there's another concept here, right? This free water clearance concept, and really the nuts and bolts of it is that we're looking to see if water is being removed from the plasma or is being added back, and it's basically a matter of comparing the concentrations of the urine to the concentration of the blood plasma, and we can see if somebody is regulating their volume, say, appropriately. And most of this would, and in my way of thinking, this is more logical than anything else. All right, in a state where somebody again is dehydrated, you'd expect ADH levels to be high and you expect the urine to concentrate, and so that makes sense. Okay, we can go over some more examples of this in the Zoom live lecture. So I will see you then.